In this screencast, we're going to talk about vector fields and how vector fields show up in nature, and we're just going to draw a little about them. So, we're going to start with matrix 2, 1, 1, 2. Every matrix represents a vector field. The way you get the vector field is you multiply by xy, and then out pops x times 2, 1 plus y times 2, 1, which is 2x plus y, x plus 2y. The idea is this gives us a function where you can put in any x and y value and get out a change in the x direction and an x plus 2y, which is now our change in the y direction. So the idea is think of this as a point. Think of this as a vector. At each point, we're going to draw this vector. So here's the idea. If I put in a point, I get out a vector. So if you put in the point 1, 0, for example, and if you put in a 1, 0 here, you get 2 plus 0, which is 2. If you put in a 1 for x and a 0 for the y, you get out a 1. Well, if I put in 1, 1, then I get out 2 plus 1 is 3, and I get out 1 plus 2 is 3. I can also put in 0, 1, which gives me 0 plus 1 is 1, 0 plus 2 is 2. While I'm at it, I'll put in negative 1, 1, which gives me negative 2 plus 1 is negative 1, and negative 1 plus 2 is 1. Let's do one more. Negative 1, 0. We're going to put in negative 1, giving us a negative 2, and then a negative 1. All right, so the idea, at these, draw this vector. At the point 1, 0, we're going to draw a vector which goes right 2, up 1. At the vector 1, 1, I'm going to draw a vector which goes right 1, 2, 3, up 3. At the point 0, 1, I'm going to draw a vector which goes right 1, up 2. At the point negative 1, 1, I'm going to draw a vector which goes left 1 more, up 1 more. At the point negative 1, 0, I'll go left 2, down 1. And we can keep on drawing. I'll just put 3 more points down. This one ends up being negative 3, 3. That one goes down a little more. It's kind of a mirror image of that. And this one heads out that way. This is our vector field. Well, in the vector field, if I were to continue drawing this vector field, you can actually see more points involved. But notice that when I put in this vector, out came a vector in the same direction. Hold on, this means I times my matrix by 1, 1, and I got out 3 times 1, 1. Well, that means 3 is an eigenvalue. And 1, 1 is an eigenvector. Similarly, the same thing happens here. When I put in negative 1, 1, I get out negative 1, 1. So a times negative 1, 1 is equal to 1 times negative 1, 1, which means here's our eigenvalue, and here's our eigenvector. This vector field, actually, if you were to continue drawing these in these directions, as long as you start on this direction, you stay in that direction forever. And if you start in this direction, you stay in that direction forever. This vector field pushes things out in that direction with kind of a strength that's 3 times bigger than the strength of pushing things out in this direction. So the idea, if I think of this as flow, if I start with some particle here, it's being pulled in this direction 3, but in this direction it's being pulled 1. So what that means is that the vector, or the point, will start to flow rather than going and continuing to move straight out. It's going to start turning until it eventually starts to follow the stronger direction. And that'll come in and give us a curve. And the same thing happens on the other side. These lines right here are called flow lines, and they describe the motion of particles that get dropped in this field. things will normally follow the bigger flow. And that right there shows us how we can actually see a physical example of eigenvalues and eigenvectors inside of a vector field. I'll let you look in the book for more examples.